Hello everyone. Welcome to our project presentation on our data structure, KD trees, and its application we implemented, that is copy move forgery detection. Our presentation starts with the introduction of our group members, explanation of our data structure, that is KD trees, explanation of suitability of data structure to this application, and demo of our application. On our project team, we have Hasan Tariq, Aqib Khan, Sameer Pervez, Ruhama Naeem, and Fizza Rubab. Our assigned data structure is k-dimensional trees, or KD trees in short. Normally, standard BSTs are just fine if we have a single feature to store in a node. But what if we have k number of features in a node? This is where KD trees come in. KD trees are simply k-dimensional BSTs where data in each node is a k-dimensional point. In KD trees, we assign each level of our tree with a dimension representing a feature. We can also call normal BSTs as one-dimensional KD trees. We traverse a KD tree the same way we do in a BST. But one thing special happens here is that we only compare the feature of our node to the level of our node is assigned. Let's understand KD tree with a simple example of two-dimensional tree having x and y as its dimensions. Now here we can see that each node has two features, that is some x and some y. Now let's see how data stores in a two-dimensional tree. We have our first node, that is 7, 2. So it will simply be added in on our first or x level. And on the graph, it will partition the space at x equal to 7 since it was added on the x level. Now, if we are adding the second point, that is 5, 4, the search for this node's correct position will start from the parent node, that is 7, 2. Since this node is at x level, so the x value of 5, 4, that is 5, will be compared to the x value of current node, that is 7. Since 5 is less than 7, therefore it will move to the left and be placed there. Now on the graph, if we see, it will partition the left side of the space, partition by preceding node, that is x equal to 7, further by y equals to 4 line, because it was placed on yth level. Now, say we are adding a third node as well, that is 4, 7. It will proceed similarly to the second one by first comparing its x value, that is 4, to the x value of current node, that is 7. Since 4 is less than 7, it will move to the left of the current node. Now, since 5, 4 is on y level of our tree, so yth value of 4, 7, that is 7, will be compared with the y value of the current node, that is 4. Since 7 is greater than 4, therefore it will move to the right and add the node there. And then on the figure, if we see, it will partition the upside of the space partitioned by y equals to 4 further into two parts by x equal to 4 line. That is because it is added on the x level. So this is how our KD tree is filled using the different comparisons or on different levels.
To attain a balanced KD tree, we need to do one thing in specific, and that is that at the time of the insertion, we check the axis of the lowest level of the tree. So for example, in a 2D tree with height 2, it would be x, then y, and then x. So the lowest level would then be x. Once we know this, we can find the median of the given vectors to be input based on their x or whatever feature, whatever axis that we have determined. This ensures a balanced tree because at each level we are splitting axis nearest to the median. Hence, we can ensure that the height of the tree would be log n. And since at its core it behaves like a binary search tree, KD trees also have O log n complexity of insertion, removal, and nearest neighbor, which is similar to find. So in nearest neighbor search, our goal is to find the point in our KD tree that has the smallest Euclidean distance from a given input point. We perform search similar to BST. However, instead of comparing the whole vector at each comparison, we compare the axis of the level of the point to the given point, as Aqib explained previously. And on the path traversed, we find the point with the lowest distance. Therefore, for any given point, we can reach either the node if it is present in our KD tree, or narrow it down to the leaf which precisely tells us where the node must lie, and therefore its ancestor node was the nearest node that we have determined to be the closest. With our selected data, the structure explained, we can finally move on to the core of our project. Forgery has been an issue since humans knew how to lie, and with the rapid development of image processing softwares, image forgery has become more and more sophisticated. One such type of forgery is where simply one takes a part of the image and copies it and moves it to another part. Aptly called copy move forgery, our program uses KD trees and nearest neighbor search to determine which part of the image has been duplicated. Now, why use KD trees? Basically, finding duplicates means we are finding parts of the image which are visually near to each other. Hence, we use the nearest neighbor algorithm, which is best applied to KD trees, which allow us to split our image into feature vectors, which can then be compared to determine which two vectors, and hence which two parts of image are nearest to each other. From where on, we can compare those parts further to determine if they are similar.
Let's now understand the algorithm for our forgery detection application. So what comes as input into our program is actually the forged image and the precision parameters, which is alpha, the value of TM, and n blocks. And we'll discuss these as we move along. First of all, our input image is converted into a grayscale image such that every pixel will now correspond to a singular intensity. Then our grayscale image is then segmented into squares of size n, which was one of our parameters, n blocks. The entire image is divided into blocks of size n. Every block is then divided into sub-blocks. Uh, Actually, every block is divided into 9 sub-blocks, and these 9 sub-blocks will provide us with our 9-dimensional feature vector. Depending upon the size of n blocks, a subblock can contain more than one pixel or a lot of pixels. So for every subblock, what we do is we sum the pixel intensities of every pixel that lie within that subblock. So for every subblock, we'll have a single summed value of the pixel intensities, such that every block will have 9 summed pixel intensity values. And for every block, there will be a feature vector that would be generated of 9 dimensions. We traverse throughout our grayscale image, which is divided into blocks of size n, and for every block, we generate a feature vector and append it to a list. At the end, the list is then used to generate our KD tree. However, as we traverse our image and we create a feature vector for every block, we add one more value to our feature vector, which is the pixel for reference, so that we know that which block is currently being accessed when duplicates are being compared and measured in the KD tree. Now that makes the number of values in our feature vector 10, but when we generate the KD tree, we input the dimensions k as 9. So the 10th value, which is the reference pixel, it does not affect the generation of the KD tree as per the 9 feature in our feature vector. After a KD tree has been generated, we now traverse over the entire list of our feature vector. Now we must understand that every feature vector in the list is actually a node in the KD tree. So for every node, we find its nearest neighbor. The nearest neighbor will actually correspond to the block whose intensities are very similar to the node that we are comparing it with. Now we found the similar blocks, but in order to make sure that they're exact duplicates of each other, we make sure that they fulfill this condition, which is that the correlation factor is less than and equal to the square of the block size multiplied by our scaling factor Tm. The correlation factor is actually the total number of pixel pairs where the sum of absolute difference between the color channels of the pixel pairs is greater than a defined value alpha. The value of alpha is chosen as per an image, the size of the image, the quality of the image, etc. We've used alpha to be 10 in our algorithm. And Tm is actually a problem-dependent threshold between 0 and 1, that is a scaling vector. So then, if the duplicates are found and they fulfill the condition, which means that they're the exact copies of each other, we make sure that the duplicate areas are colored white in our output image and are identified in the picture. It should be noticed here, however, that the precision of our output image will depend upon the size of the blocks that we define while giving as parameter to our program. The smaller the value of the n blocks, more detailed will be the highlight of the duplicated areas in our output image. Because the smaller the n blocks, smaller will be the sub blocks, and that would allow for the pixels to stand out individually. And thus, our output image will be more pixelated and will help us identify the individual pixels even. For example, if you see in our outputs, it can be seen that our outputs are actually very precise. But in order to achieve such precise outputs, there was a trade-off with the processing time because here the n block size that we took was 9, which means that every sub-block was size of 1 pixel. Traversing over the entire image will take a lot of time, and it actually did. But the outputs are very precise, that is per the quota of a single pixel. The duplicated areas are identified as per every pixel that is same. However, for larger block sizes, even though our outputs aren't as precise, they do a pretty good job of identifying the forged areas and giving us a bigger picture of where our forged areas in the picture lie, which could be used for basic purposes. And such precision is only required in very professional or high level processing. Thank you.
After successful attempts of using KD trees in image processing and forgery detection, we thought of playing around with them a bit more. Through research, we got introduced to the field of generative art, that is basically art through programming and coding. Generative art takes full advantage of everything that computing has to offer and produces elegant and compelling artworks such as the one you see in the bottom right corner of the screen right now. So we tried to do the same, but using KD trees instead, and we used R, which is a statistical programming language that has remarkable ready-to-use packages for making generative art. So the general outline of making images is as follows. We first deployed the two libraries, that is MathArt and ggplot packages of R programming language, and we sampled random 2D points. The number could be anything according to the image we want to make. And then later, a KD tree is built out of those points using a built-in function. It outputs a data frame that has the coordinates of the point, as well as the endpoint coordinates of the corresponding segment that has to be on the plot. So once we obtain this data frame, we can simply use the ggplot library to plot those points and the segments, and we can obtain art like these. And of course, we can tweak the parameters, change the line colors, line types, line sizes, and generate art as much as we want to and however we want it to be. So these are two images of our KD art library. So the first one is the KD donut. In this, we have created random points that are sampled onto the equation of a circle, and the radius varies between the donut size that you can see in the image right there, and you can see the KD tree pattern going on inside to create a halo of yellow perpendicular lines. And in the second image, we have made a KD orbit. This is basically when we have created points that are mapped, random points that are mapped onto the equation of an ellipse, and the equation of the ellipse has been shifted by a few units. So that is what we end up with. And to look at more of the images, I suggest you guys visit our website or watch in the demo where we have uploaded the rest of the images as well.
So we decided to build a web application to host our project. We're using Django on our server side and React.js on our client side. Okay, so this is where we detect for forgery. We will first input an image and then we will put in some parameters. And then we will allow and submit. Okay, so this will take some time. Meanwhile, we can check out the rest of the website. So this is a basic explanation of what KD trees are, some complexity of it, and then we have some visualization. Yes. Next, we have a gallery that shows recent images, and then we have generative art, what Fizza just told you about. Okay, so this shows how we were able to make these art images, and then this showcases a couple of images that we were able to generate. Then we have an about us page that shows a division of labor, and we can finally head back to the code. Okay, so this is the class of KD tree that we are using to basically do most of our algorithm. Yes. So we have things like display, k build, kd build, and then we have nearest distance, and then knn. this is about it. This is being called in main.py right here. In this detect forgery method, we are basically we have a path as an input, and then we are returning an output path. This method is being used in our API, our backend API in Django, right here. So when we have an entry in our database, we first save the image. We first save the entry with the input image, and then when we don't have an output image, we apply this method on our input image, and then we receive this output image, and then we save this again. Then we have this React part that I'm not gonna explain right now. Okay, so I think it might have been, yes. It is ready now, so we can see that it is being detected. I mean, yes, it is being detected. So this is about it, and thank you.
And that is all for our presentation on our project. Hope you enjoyed it.